ಯಾಕೆ ನನಗಿಲ್ಲ ಆಗ್ತದೆ. ಹ್ಮ್ ಯಾವ ಸಣ್ಣ ಇಡ್ಬೇಕಾದ್ರ ಹಲೋ ಹಲೋ
Hello, yes, sir.
ಓಕೆ ಸೊ ಐ ಆಮ್ ಆಡಿಬಲ್ ಆಲ್ ರೈಟ್
Good afternoon, Pastor. Sure.
Good afternoon. Yes.
We got the link now.
Okay.
Yeah.
Yeah. So we are ready.
More or less ready. So
Uh,
I think we can start actually, right?
we can start. All the how many people are there?
People started joining little late also. They continue joining. A few have
Okay.
joined. So
So you want to give few minutes or what? What we should do?
2 minutes, maybe 2 minutes you give and then start.
Okay. Okay. So I will come back in 2 minutes. Huh?
Okay, fine. Hello, go ahead. Yeah, how many joined? Huh? 10 on WebEx. Okay. And yeah, YouTube 10, 10. Around 20, no? Okay, fine. Professor Harshul was asking how many joined. I think you can start now, right? Okay, thank you. You coordinate, huh? Okay.
Okay. So I am back.
Professor Harshul,
Yeah.
you may start. Around 20 person has joined already.
Okay.
So maybe you can start. These are roughly 20, 25. They are the regular attendance. And then
Okay.
some check in the YouTube actually afterwards.
I
That
see.
is the way. So it's average. It is like that only.
Okay.
Let's
So
start, sir.
I share now. Share my screen.
Yeah, you please share the screen.
Share content. Yeah, what is the content?
Hello, Rohit.
Where is
Starting
it?
to
No, again, it is not sharing. You are sharing your screen.
Sir, just open the PPT file. That's it. We can see your screen. Only the PPT file is. You have to.
Oh,
You have
I see.
minimized.
Okay.
Yeah.
I see. I see. Okay, so I just open my PPT file. Okay, is that fine?
Okay. So make it full screen. Then it is fine, sir.
Then what is on the top? This one is still there.
So that will go. You just don't put a mouse over there, mouse pointer over there. It will go automatically. Yeah, it is fine now, sir.
It's fine. But
Yeah, just
it's coming on my screen.
no.
That
Just click on, sir. Just click the mouse elsewhere somewhere. It will go automatically.
no, it is moving. The slide is moving, but that thing is this thing is not gone. This thing should go, no? Hide meeting controls. What is this?
That is just a
Speaking
control to stop sharing and all such options like mute, etc.
speaker video view. Arey, hide window. Hide window. I should close hide window. Okay, that is gone. Now stop this pause sharing. This is mute. And what is this? You are streaming the meeting to YouTube. Why this? I don't want this on my screen. How do I? No. This is coming on the front of my desk, sitting in front of me.
who is helping? Anurag is there.
Sir,
Anurag.
I have to remove this from the.
sir, that will go automatically. You just need to click somewhere else, sir. Don't drag your mouse pointer on that thing. No, it will come back to back
Yeah,
again.
clip somewhere else only. Now the next slide has come.
So you just need to
Slide
go. So you can just use the arrow button to go to the first slides. That's it. It will go
Okay, this is the
automatically.
arrow button. I'm on the first slide,
Yeah.
but that copy of that slide is that the screen inside screen is coming. No.
Professor Hushura, in my
Okay, okay,
screen.
okay. Sir, do one thing, sir. Just right click, and maybe you would have entered into presentation view of the PPT. No, no, that is fine, sir. I think,
That slide inside slide, the main slide, the copy of that is appearing again. It's there.
okay, just press Alt Tab together. You're using MacBook, sir?
Huh? No, not
Are
MacBook.
you,
It's a laptop.
okay, so just press Alt Tab and just open the presentation view.
This is not. It has come twice. No, my God. It has gone out of the full screen mode. Okay, now we go to the full screen view. Full screen, but then that is still sitting over there.
Which one is sitting, sir? I think in my screen, nothing is. Everything is all right. Looks like.
You see, in my screen, the first slide is appearing again inside another window. You're sharing, so I stop sharing and then do it again.
Sir, if you stop sharing, we won't be able to see.
But how do I remove this pause sharing? What is this? See, I have another window. I will show you what I'm seeing.
Yeah, sir.
I will call on video call and then I will show you that.
Hello. Huh? Hmm.
Okay, I have called. Can you see what I'm
Professor
showing you my
Hushur?
screen?
Professor Hushur?
Can you see me? Hello?
Yeah. Hello.
Yeah.
Uh, in my screen, it is coming all right. So if you having any problem, then in that case, can you send the PPT file to our this email ID so that it can be shared from here? That will be
No, no, you are
okay.
sharing your screen.
In my
No,
screen,
I am doing a video call to you.
Mhm.
Okay, it has gone. It has gone. Okay, fine.
It has gone
Now I
now.
have. Yeah, now it is fine. You were
Okay.
sharing on the
My
top. It was
screen.
something was there. Okay, fine. All right. So
All right.
let us begin. Okay. Good afternoon, everybody, and we are starting this the second module now, heteronuclear and multidimensional NMR.
Sir, click on screen, sir, once.
Okay. See, I mean, why heteronuclear NMR? So this question, NMR has been, I mean, the basic principles of NMR have been covered in the previous lectures. I have seen those contents which were shared, and quite extensively the fundamental principles have been covered, various aspects. I will try to be continuing from that, and maybe there may be sometimes there can be some repetitions, but it should not matter. It will only consolidate the ideas, and it may be required for my continuous interaction. So for my continuity, some of those things may be required, so, but I think that should not matter. So you see, most elements in the periodic table, you can read this here, right? Most elements in the periodic table have one or the other isotope whose nuclei have magnetic moment and hence are NMR accessible. This is the big thing. We have seen in the previous lectures that NMR is a very insensitive technique, and it is compared to optical spectroscopy, this is very, very low sensitivity. And indeed, yes, that is true. Even so, the NMR has become an indispensable technique for various, in all areas of, say, science. And that is because of a couple of reasons. One of the things is that there are so many probes available to you. There are so many elements in the periodic table, and every one of them has one or the other isotope which has a magnetic moment, and therefore it becomes NMR active. There may be some which have quadrupole moments and things like that, but those ones are not so useful. But those which are routinely accessed are things like proton, carbon, nitrogen, phosphorus, fluorine, and so many of such ones are there. So therefore, it provides many, many different probes for us to investigate any kind of a system we would like to study. That's why it has become such an indispensable tool in chemistry, biology, material science, and medicine. And you can see already that NMR has won 7 Nobel Prizes. And there are earlier Nobel Prizes were in physics, then there were in chemistry, then there were in physiology and medicine. Therefore, it has become such an indispensable tool, despite the fact that it is a low sensitive technique. Okay. Further, this low sensitivity is a consequence of a weak interaction between the nuclei and the surroundings. In fact, this is a boon in disguise. Because of the weak interaction, how do you know it is a weak interaction? Because we know that we are dealing with radio frequencies. Radio frequency is one of the low frequencies, and therefore its interaction is obviously weak, which means that it does not interact very strongly with the surroundings. And that means that whatever information you are getting is exclusively on the particular molecule or something which you are studying, and it is not complicated by the presence of various other elements which are not wanted for you. Therefore, the interpretation of the data also becomes extremely easy. Okay, so let me revisit this chemical shift, and this has been discussed extensively. I have seen it. Basically, to say that if you have a magnetic field to a nucleus, there is an electronic cloud around the nucleus, and this electronic cloud screens the externally applied magnetic field, and that is given by this kind of an equation. The field seen by the nucleus I, which is Bi, is equal to B naught, which is the external field applied, multiplied by 1 minus sigma I, and sigma I is called as the screening constant. Screening constant which reflects the environment of the nucleus. That's the local environment, the electron cloud and things like that. And this interaction energy in terms of frequencies, you can write as nu I is equal to nu I is minus gamma bi divided by 2 pi. Gamma is the constant known as gyromagnetic ratio, which is unique to every nucleus, and that distinguishes one nucleus from another nucleus. And then here you have you express this to get an information exclusively on the surroundings or the particular molecule which you are considering the electronic cloud around it. You want to know about the screening constant because this is very characteristic of the electronic environment around the nucleus. And you want to remove the field dependence of this and make it exclusively dependent on the screening constant. You define a quantity called as delta, which is defined as by this equation here, nu I minus nu r divided by nu naught. Nu naught is the spectrometer frequency, and nu r is some reference frequency. Reference your observed frequency of absorption, NMR absorption, to a particular reference compound, so that, and then divided by nu naught, which is the spectrometer frequency. This is gamma b naught. Then it will not be unitless because this has no units, and this will now be in ppms. That's why you have this 10 to the power 6. Nu I minus nu r is in kilohertz. Nu naught will be in megahertz, several megahertz. Therefore, you need to multiply by 10 to the power 6 to get a number which is of the order of few tens of hundreds and things like that, and that is the ppm. And higher delta implies higher BI, implicating downfield shift and vice versa. This is shielding. You talk about shielding and deshielding, and therefore you call them as downfield shift or upfield shift compared to a reference compound. All this has been discussed extensively. We don't want to touch too much on that. Some standard properties of some common nuclei I have listed here. These are the nuclear spin and related data on some chosen nuclei. As you know, proton is the most sensitive nucleus among all of this because it has the highest gyromagnetic ratio. Magnetic ratio determines the interaction energy with the given field, and therefore whichever one has the high magnetogyromagnetic ratio is the most sensitive nucleus. The proton has the highest sensitivity, and it has a gyromagnetic ratio, as you can see, is the largest among the certain nuclei which I have listed here. And then you have the deuterium, the carbon 13, nitrogen 15, nitrogen 14, and that is also nitrogen 15, and then the fluorine and phosphorus. Of course, there are the whole list, as I said, periodic table, every one of them has one or the other isotope which is useful. And a particular magnetic field of 11.74 Tesla here I've chosen here. Here the spectrometer frequencies are given in the numbers. Proton is at 500 megahertz. That particular magnetic field which corresponds to gamma B naught is equal to 11.74 Tesla. B naught is 11.74 Tesla. Then the spectrometer frequency for proton will be 500, and it is 76.7 for deuterium, 125 for carbon 13. Notice carbon 12 does not have magnetic moment. Therefore, you have to go to carbon 13. And then you have the nitrogen 15, which is 50.68, and nitrogen 14 is 36. Fluorine is very close to proton, 470, and phosphorus is 202. So in order of the frequencies, if you can see the gammas, proton is the highest, and this is followed by fluorine, then it is followed by phosphorus, then it is carbon 13, and then of course it goes down. And now, as I said, we have to also look at the natural abundances. Among these, the proton has the highest natural abundance, 100% natural abundance we take. Fluorine also is 100% natural abundance, but the carbon 13 is only 1.1%, and nitrogen 15 is 0.37%. Of course, nitrogen 14 is 99.6%, but for nitrogen 14 has a spin 1, which means it has a quadrupole moment, and often that can lead to very rapid relaxation phenomena, and we would not like to deal with nuclei which have quadrupole moments. And that's why we choose nitrogen 15, but its natural abundance is only 0.37%. So in order to make good use of those, of course, we'll have to do something else to enrich the system with nitrogen 15 and so on. We will come to that a little bit later. Similarly with carbon 13. Carbon 13 is only 1.1%. Okay. And all of these have a wide range of chemical shifts. Okay. And as I said, we have chemical shifts are determined by comparing them with certain absorption energies with respect to certain reference compounds. The NUR is the reference compound. And we have different kinds of reference compounds used here. And that is for proton, you have different kinds of reference compounds. Tetramethylsilane, TMS is used in case you have a solvent which is non-polar, and you also use TSP in case of a polar solvent. The DSS is also used for polar solvents. Acetonitrile, dioxane, tertiary butanol, tetramethylammonium chloride, all various kinds of things which you can use for the protein. Ammonium chloride, the methyl is used. And you have for carbon 30, and again the TMS, TSP, and DSS. For nitrogen 15, you use ammonium chloride or ammonia, and phosphorus 31 use 85% phosphoric acid. All of these are their resonances are taken to be at 0 ppm. Okay, with respect to the TMS, some of these standards also have a certain chemical shift. For example, you see dioxane appears at 3.64 ppm with respect to the TMS. Tertiary butanol appears as 1.27. Tetramethylammonium chloride appears as 3.1. And these ones, you can use them as references, all right, but they are not at 0. But most of the things are at 0. So if you use those ones, your chemical shifts will be directly with respect to that, the given number. Okay. Here is the range of chemical shifts for the different nuclei. I show you for a few of those which are most commonly used for chemistry and biology. The proton chemical shift ranges here are indicated depending upon the various structures of the molecules. 0 ppm is, like I said, is the reference compound. If you have saturated molecules, then you have the things appearing at between 1 to 2 ppm. Allylic groups also appear there. Then you have the ROH group. ROH, this appears with a wide range of chemical shifts over there, depends upon the various kinds of substituents over there. Then you have the CH2X, CH2O, CH2N. In all this, we are talking about the protons, okay? We are talking about the protons. Depending upon what the X, O, N or things like that, you have a wide range of chemical shifts there. The vinylic appears at particular between 5 and 4.5 to 6.5. Aromatics appear between 7 to 8. Okay, and then the aldehydes are CHO. Such a huge tables are made. I only listed here a certain common ones which are there in organic chemistry, we encounter in organic chemistry. The carboxylic appears at a much lower field. And if you go to molecules like DNA and things like that, hydrogen bonded systems, they will go to beyond 14 ppm, 14, 15, 16 ppm. Also, you will see when there is hydrogen bonds. Amide groups appear between 8 to 9. These are in the proteins and things like that. You will see in the 8 to 10 ppm or 7 to 10 ppm. Aromatics appear there, amino groups. So this list is not exhaustive. This is only indicative. The nitrogen 15 chemical shifts. This is the wide range from it is up to 800 ppm. Depending upon the structure of the group, structure of the molecule, what you have. You have the amines, the ureas, amides, nitriles, indoles, pyrols, azide center, pyridines. See, on the basis of the chemical shift itself, you can kind of identify what sort of a group you might be encountering. Up to 800 ppm, you see the huge range. It is a huge range of chemical shifts you have. That is again quite an advantageous thing. Proton is going only up to 14, 15 ppm, but nitrogen is going up to 800 ppm. This is a huge range. And carbon is again going up to 250 ppm. See, and you see different kinds of carbons, or the ones which are observing are they are colored red. Okay, this chemical shift belongs to that red colored nucleus. Okay, so depending upon what sort of a substituent you have, what sort of a group is attached to this carbon, you have a wide range of chemical shifts, goes up to 250 ppm. Typically, looking at the chemical shift, you start concluding, okay, this must be this particular group. This is the nitrile group, or CONR2, esters, carboxylic acids, like the ethylenic groups, hydrocarbons, okay, as various ketones, aldehydes. All of these appear at distinct chemical shifts, and that is extremely useful parameter from the structural chemistry point of view. Okay, now next important thing to notice is that relative sensitivities of these various nuclei. The chemical shifts, wide range of chemical shifts is one thing, but the sensitivity is another issue. The relative sensitivity means given the same number of nuclei, what are the intrinsic sensitivities? This obviously depends upon the gyromagnetic ratio because that is the one which interacts with the magnetic field. Now, typically it is said that relative sensitivity is proportional to the third power of the gyromagnetic ratio. So if I take the proton as my standard, if I call the proton relative sensitivity as 1.0, what are the sensitivities of the other nuclei? For example, if I take deuterium, its sensitivity is 0.0036. This is the relative sensitivity. How do I get this? I take the gyromagnetic ratio of deuterium divided by the gyromagnetic ratio of proton and take the third power. Okay. Why third power? This comes from the theory of analysis of interactions and things like that. Practically, there are certain facts which are not quite well taken care in that sense. So therefore, often we say it is 10 to the third power, but practically it has been observed it is actually the power of 3 by 2. Often it is you end up at a power of 3 by 2. Nonetheless, this is the kind of a this which comes from the theoretical analysis of the interaction between the nuclei, and it is quite indicative. Carbon 13 is 0.0159. Remember, this is considering equal number of nuclei. In a sample, if you have equal number of nuclei, equal number of proton, equal number of carbon 13, what will be the relative sensitivity? And nitrogen 15 is 0.001, is extremely small. And this is, and F19 is 0.83, which is very close to the proton. And phosphorus 31 is 0.067, 0.066, and it is also quite low. And the spectrometer frequencies are also given. If the proton is at 100 megahertz, you'll have the deuterium at 15 megahertz. That's because it is almost 1/6 of the gyromagnetic ratio. Carbon is 25 megahertz. That is 1/4 of the proton. Nitrogen 15 is 10. That means it is 1/10 of the proton. That is the gyromagnetic ratio. And F19 is almost same as the proton. And phosphorus 31 is 1 by 2.5. So 2.5 times. So 40.48 megahertz. And absolute sensitivity will be relative sensitivity multiplied by natural abundance. So here this number is given considering the gyromagnetic ratios alone, considering equal number of nuclei, but all are not equally abundant. Therefore, you have to multiply by the natural abundance to get the absolute sensitivity. Therefore, you can see the sensitivities are vary quite a lot from nucleus to nucleus. Proton is the highest of all the nuclei. Okay. Now, this also has been discussed in the previous lectures I saw. And when the system is very low, in the early days of those, the CWNMR was used. You scan the magnetic field or scan the frequency, by and large the magnetic field, to obtain the resonance condition for a given line. However, that becomes absolutely impossible when you want to consider such low sensitive nuclei and issues of that type. And therefore, a new method was developed that led to the Fourier transform NMR. Here is considered the pulsed excitation. Excitation is done by applying the radio frequency for a short time, and that is indicated schematically here. So you have the radio frequency applied for a short time, the radio frequency here, and switch off the radio frequency here. And this short time, this is approximately of the order of few microseconds. Okay, and then the response of such a kind of a pulse in the frequency domain will generate a kind of frequencies like this. So there is a Fourier relationship between these two. The time domain signal here, time domain function what we have here, and it is related. In other words, it is like applying a larger number of oscillators at the same time. If I apply a radio frequency for a short time, then it is equivalent for me to generating so many radio oscillators, generating individually different frequencies, and so many frequencies are generated, and they all have different amplitudes. On the vertical axis, what you have here is the amplitude. All these frequencies are generated with the different amplitudes. The main frequency is here at omega naught. This has the maximum amplitude, and all others which are generated will have different amplitudes here. But this range is quite wide. You can see here this point comes at 1 by tau. approximately 10 to the power 5 hertz. That is 10 to the 10 megahertz, 10 to the power 5. Okay, so this is a huge number, 100 kilohertz. So this is 100 kilohertz on this side, 100 kilohertz on this side. This is a large number. Okay, but we want to have a uniform amplitude for our NMR spectra, that you excite the nuclei to the same level, because the excitation depends on the power of the RF which you apply. Okay, and therefore what one does is one chooses a small region here between this from here to here, which may be about 5 kilohertz on each side or 10 kilohertz on each side, which is sufficient. And then all of them have identical amplitudes, therefore identical power is applied. So all these frequencies are applied at the same time to the system. So you don't acquire the data in a sequential manner from one resonance to another resonance. You excite all of them at the same time. And the detection system is again very simple, in the sense that we have to look at what the pulse does to the magnetization. We all have seen in the previous lectures, the equilibrium magnetization of a given system will be along the z-axis, because the field is along the z-axis, and that equilibrium magnetization is given by m0. There is no magnetization in the transverse plane. All the equilibrium magnetization is along the z-axis. The application of the RF pulse tilts the magnetization out of the z-axis. So therefore it causes a rotation. It causes the rotation of the magnetization from the z-axis towards the transverse plane, either onto the y-axis or onto the x-axis. So it goes orthogonal. If you apply an RF along the x-axis, magnetization rotates in the YZ plane and goes to the y-axis, or so on and so forth. If you apply a pulse along the y-axis, it rotates into the xz plane and it can come to the x-axis. It causes the rotation. So that rotation angle is given by this here, minus gamma h1 tau. Tau is the pulse width, that is the time for which you apply the RF, and h1 is the amplitude of the RF which you apply. If this one is equal to 90 degrees, then the magnetization rotates out of the z-axis by 90 degrees, which means it may come onto the x-axis if the RF is applied along the y-axis. It will come onto the y-axis if the RF is applied along the x-axis. What happens then? Okay, this is schematically indicated here. So you consider two spins here, K and L, and equilibrium magnetization initially is along the z-axis, and you apply a 90x pulse, and this both of these now get rotated into the y-axis here, and this magnetization is represented by these two operators here, IKY, ILY. This represent the Y magnetization of the two individuals. Now once the pulse is removed, the system will have to go back to equilibrium. They will start processing with their magnetic characteristic frequencies and recover along the z-axis. There are two things which are happening here. One is Z magnetization recovery. Z magnetization recovery is characterized by the T1 relaxation, that is the spin lattice relaxation. There is also decay of the transverse magnetization because of the T2 relaxation. Both the things are happening here. When the recovery is happening, both the things are happening there. The signal which you detect will be along in the transverse plane. So that signal which you indicated here is given by the sum of these two cosine terms here, because they are processing with the cosine with the frequency, and therefore they induce a signal which is proportional to the cosine term. So the signal will be IKY cosine omega t plus ILY cosine omega t, but the relaxation part is not written here. So therefore the relaxation, you have to multiply it by e to the minus t by t2 for the FID, for the signal, and that is indicated here as a FID. So the FID is a transverse magnetization, and that is decaying with time because of the individual transverse relaxation, the T2 relaxations. Okay, now therefore the signal what you are getting is a superposition of the contributions from the various spins, and therefore in one go you have a time domain function which is f of t, and therefore it is related to the frequency domain function by a Fourier transform. In the same manner as we did earlier, the excitation is related, the pulse is a time domain function is related to the excitation and the frequency domain function. Here the signal, which is a time domain function, is related to the frequency domain which represents the NMR spectrum. Therefore, in one go, you are able to collect all the signals, all the frequencies. So which means that you have a substantial gain in the signal to noise, because you can collect several scans co-add them. In the case of sweeping methods, this is impractical because it will take a huge amount of time, heavy demand on the spectrometer stability, magnetic field stability, etc., etc. And that is why it was not possible to study any of these low sensitive nuclei, the heteronuclei in general. Only proton was the focus at that time. With the development of this, now this is the so-called Fourier transform NMR. This was the first NMR revolution. This actually led to various other developments because it also separated the excitation of the pulses, excitation of the splints from the detection of the response. When you are detecting the signal, there is no self in the same amount of time. You have got the top spectrum is the Fourier transform spectrum and the bottom spectrum is the CW spectrum of the same molecule. Okay, so let's move on to the next thing, and that is with respect to the couplings. There are various kinds of, we were focusing on the carbon 13 here, let us say. Okay, so if there is a carbon which is not attached to any proton, it will have a single line there. If it attaches to one proton, it is split into two, and the center of the chemical shift is here, and this is plus, on the this side is plus J by 2, and it is minus J by 2. Okay, now if you have the CH2 group, there are two splittings because there are two couplings, and the coupling constants are identical. So you get 1:2:1 pattern, and there is a separation of J from the center in either direction. So delta nu plus J here, and delta nu minus J here. So CH3 group likewise will have three splittings, and the three splittings will result in a pattern of 4 lines which have the intensity ratio 1:3:3:1. And the center is again at this point. Center is here. This is the delta nu. You have plus J by 2, minus J by 2, and this is minus 3J by 2, and this is plus 3J by 2. So notice from here to here it is 1J, here to here is another J, here to here is another J. So you have 3 J's here. And similarly here also, from here to here it is J, here to here is J. Okay. So remember this because this will be useful when we are actually going to discuss more other experiments. Okay. Now, for chemistry, C13 NMR plays a very important role. Okay. So often we want to know how many carbons are there in normal. You synthesized a new compound, and you want to see whether you synthesize the right compound, whether it has enough number of the desired number of carbons what you have. So you would like to see the carbon spectrum and without any complications. Therefore, what one does in that situation is you decouple all the protons. Decouple all the protons. There is a process known as broadband decoupling. You can do broadband decoupling. When you decouple, that means all the protons are decoupled. All the carbons are decoupled from the attached protons. Okay, in that case, what you will get one line per carbon. And for example, for this molecule which is here, how many carbons are there here? 1, 2, 3, 4, 5. So there are 5 carbons, and you can actually see 5. And this is of course your reference, the reference compound, and you have 5 carbons in there: 1, 2, 3, 4, and 5. However, these intensities are not identical. Often this happens in C13 NMR. Intensities are not quite reliable because you collect the data in such a way that you don't optimize for the intensities to be the same. But here it doesn't matter. You only want to count the number of signals, and that is what it is. However, in the process, what has happened is you also lost the multiplet information of the carbon. But the multiplet information may be useful. If you look at this broadband decoupled spectrum, you do not know what kind of a carbon it is. Whether it is a CH or a CH2 or a CH3, what it is, you don't know. Right? Therefore, multiplet information is required. If you have a CH3, you will get a 1:3:3:1 quartet. The CH2, 1:2:1 a triplet. CH, you get a doublet. So that information is lost here. But you want to retain that and yet get a good dispersion in the spectrum. And then often what one does is you do what is called as off-resonance decoupled spectrum. Off-resonance decoupling meaning what? So corresponding to the C13 spectrum, there will also be a proton spectrum of the same molecule. Okay. The proton spectrum of when you do selective decoupling, what you do is you put the decoupler power, the decoupler frequency on the particular proton frequency. So if I have a triplet of a carbon and the corresponding proton spectral frequency at a particular ppm value, let us say, suppose the carbon is at 60 ppm and the proton corresponding to that is 4 ppm on the proton channel, on the proton spectrum. Now you keep your decoupler field at 4 ppm and decouple it so that that particular carbon gets decoupled, and that is this broadband that is actually a selective decoupling. Now broadband decoupling techniques are available where you can irradiate all the protons in one go with similar power, so therefore you get a broadband decoupled spectrum. Now what you want to do is you want to get the coupled spectrum, but yet we want to obtain a resolution enhancement. You want to modulate the coupling constant so the triplet pattern is not lost, but the lines appear narrower. In which case what you do is you keep your proton frequency far away from the spectral region. So which means if let us say your spectral region is 0 to 5 ppm in the proton, so you keep your off resonance of B2 field, which is the proton field, at let us say about 5 ppm, something like that. So therefore, it is a different offset from different proton group. Okay. So therefore, it has a different offset. That is the delta nu. Delta nu is the offset from the resonance. And so it is different from different ones. And then what happens is the particular the different protons are irradiated with the different powers because of the offset, and there that will cause a reduction in the coupling constant of carbon and proton, and that is indicated by here by this equation here. There is a reduced coupling constant of the proton of the carbon proton coupling, and that is given by this equation, which is the not reduced JCH original one, delta nu, which is the offset, divided by B2. B2 is the in of course we are talking in terms of the frequency units. Okay, B2 is not in terms of Gauss, but it's in the frequency units. So when you do that, the multiplet pattern will be retained, but the coupling constants inside will be changed. So you get a spectrum which is like this. Now you see this fellow, you are getting a 1:2:1 triplet here, which means this carbon is a CH2 group. Similarly, this carbon what you have here, this is also a CH2 group, and what about this? These are also CH2 groups, and this one is the singlet. It is no change at all. So which is this? So obviously this carbon must be this. So this has no proton attached. All others are CH2 groups, and therefore all others are triplets. So you can see that this kind of information is obtained from this kind of an off resonance spectrum. So here is another example there of comparison of decoupled off resonance decoupled spectra. So you have the CH coupling when there is a full spectrum without decoupling. So you have here a quartet 1:3:1, and here is, of course, this is the solvent CDCl3. This comes from the CDCl3. Okay, and here is a doublet, and a singlet. So you have 4 carbons. Okay, 4 carbons, and that is indicated by this. Okay, you have 4 carbons here indicated by this. Now in the off resonance, you can see this doublet appears as a doublet, but the reduced coupling. This also appears as a reduced coupling. Okay, so and this one is a singlet. Nothing happens to it, remains as it is. And this one is a triplet. So therefore, see 1:3:3:1. This is therefore this is a CH3 group. This is a CH group, a singlet, and you can easily correspond that here. You see, one is so you can see one. This is a singlet. This is also at the highest chemical shift. That also we have seen. Chemical shift also indicates what sort of a group it must be. This is the carbonyl carboxyl group, so far down there. And then you have the 2 other CH groups, and those are both are doublets because they are coupled to. Notice here we are talking about 1 bond couplings. Other couplings are not relevant here because the 1 bond couplings are very large compared to 2 bonds and 3 bond couplings. Therefore, they don't show up. We don't see that kind of a resolution here. This multiplicity what we are showing is basically because of 1 bond couplings. Okay. Therefore, the CHs which are here, these are 1 bond doublets, and these 2 centers which are presented, this is doublet there. doublet here, and the reduced doublet here. And then, of course, you can therefore identify which group is what. Okay, this is yet another example of the same thing. Very complicated systems which are there, you will not be able to figure out in case you have. Then this is a fully decoupled and off resonance decoupled spectra. So this is the molecule here. You can see this. There is various kinds of carbons. Okay, then the methylenes here. So 3, 4 along this 3 and 4 are the two methylene groups there. So CH2 groups. So there are two triplets here. Two triplets appearing in this, and they are coming as singlets in the decoupled spectrum, methylenes. Then this epoxide, this is there is number 1, that is also CH2 that appears in the middle here. This is also a CH2 group here, and then the 2 is there is a doublet. 2 is a doublet that appears here. This, of course, is your CDCl3, and you have a 1:2:1 triplet, and this is your number 6. Number 6, this is this, there is a CH2 here, and then the 5 is a doublet, and that is this one. This is the CH group here. Okay, so therefore, by looking at this off resonance decoupled spectra and the decoupled spectra, you can figure out which group is what and how many carbons are present inside this. Okay, and that is so much now for the nature, quality of the spectra, how to extract the information on heteronuclei. Similar things will appear for other nuclei as well. And we are talking about the carbon-13 spectrum because this is the one which is mostly used by various people. Okay, so now I move to another topic which is known as the spin echo, which is very fundamental in most modern experiments, more sophisticated experiments, and this also might have been discussed briefly in the previous lectures. And what is this? What is a spin echo? This indicates that. Okay, now here you have a pulse sequence is given by 90 degree, then there is a tau period t, then there is a 180 degree pulse, then again the same tau, and then you have the signal coming back as an echo. Okay, so when you apply the 90 degree pulse, okay, let's watch the top there. So it starts dephasing. When it is dephasing, the signal is decaying, and after the 180 degree pulse, they start rephasing once more. Once they rephase, then the signal is back in together, and that means it is an echo. So it is similar to what you hear in the sound echoes. When you go and it comes back to you, there is an echo. So in the same manner, initially the 90 degree pulse causes transverse magnetization. The transverse magnetization dephases as the nuclei start precessing around the z-axis. And when you apply the 180 degree pulse, there is a rotation of all of those. And when they continue to start moving in the same directions, they will refocus. And when they refocus, that is the echo magnetization will all come together, and that you will have an echo. So this is the spin echo. This was discovered by Hahn way back in 1950s, and this has become an independent, very important ingredient of all multiple sequences. Notice here the spins which are there, they are at different frequencies. Okay, that's why there is so much of even if there is a single frequency, the dephasing can occur because of the spin-spin interaction. The dephasing will occur if there are frequencies of different nuclei, different protons, for example. So there is a there is a CH proton or a CH2 proton or something, or the proton attached to the amide, proton attached to carbon, things like that. They are different frequencies, and they all persist with the different frequencies. Okay, so even in the let's say we are talking about one particular channel, the carbon proton frequencies. Okay, attached to the at one proton at 5 ppm, another proton at 7 ppm, third proton at 8 ppm. Okay, all of you apply a hard 90 degree pulse, so it will bring all of them onto the transverse plane. Now all of them get refocused there, right? At the end of 2t period, all of them get refocused. What is the meaning of this? Therefore, the echo amplitude is not dependent on the frequencies at all, of the individual frequencies at all. Full magnetization is recovered. Therefore, what we say is the chemical shifts are refocused. So when this happens, the chemical shift information of the individual nuclei is lost at the time of the echo, as if there was no. However, the amplitude of the echo will not be the same as the initial magnetization, because during this 2 period, 2 tau, 2t, there will be decay of the magnetization due to transverse relaxation, the T2 relaxation, and that will cause a small decay of the signal, and that will reflect in the echo amplitude. Okay. In fact, this phenomenon can be used measure the transverse relaxation times. Okay, that is exactly what happens. I will show you in the next slide. You can see here, this is the kind of an FID during the spin echo. So once you apply the first 180-degree pulse, then the signal starts dephasing, then it will start decaying. Okay, the FID, this is my FID, all the various things, initial FID. And then at the center here, a 180-degree pulse is applied. And as you progress after the 180-degree pulse, this spin system, they start refocusing there, and then at 120 milliseconds, not 120 milliseconds, at time somewhere here, so the echo is appearing. Notice this echo amplitude is not the same as the amplitude here, the beginning magnetization. Okay, the magnetization is decayed, and this decay happens because of the T2 relaxation. And if you fit this to an exponential decay, you will find that the decay is T2 is 120 milliseconds. The spin echo is happening at about 100 milliseconds through this time along the time axis. This is T2 star. T2 star is 20. What is the T2 star? T2 star is this relaxation, T2 relaxation plus the line broadening because of inhomogeneities. If there are magnetic field inhomogeneities in your system, that contributes to the dephasing of the spins, that is effectively producing different frequencies of precession, right? And that will actually cause a dephasing of the signal much faster, and that T2 star causes a rapid decay of the signal, and it has decayed here because of the T2 star. Okay, now then when it refocuses, all these field inhomogeneities are also getting refocused, and what comes out here is the echo. And this echo amplitude is decayed from original amplitude, and that is because of pure T2. It is not T2. The field inhomogeneities are not there. They are not contributing. Okay, they are refocused. Field inhomogeneities are refocused. Chemical shifts are refocused. Okay, when we say chemical shifts are refocused, it automatically implies that the field inhomogeneities are refocused. And therefore, this is a typical picture you will get in the FID when you do a spin echo experiment. Okay, therefore, spin echo refocuses chemical shifts. The spin echo refocuses field inhomogeneities. Okay, so what can we use this for? As I said earlier, this you can actually use to measure the T2s. See, this is indicated there. So as you increase the T, what happens? You are giving more time for the system to decay. So the T2 relaxation is operating there. When the T2 relaxation is operating, the spin system, the spins are, the transverse magnetization is decaying. But therefore, the echo amplitude also decays. So look at this carefully several times. As we increase the T, the echo amplitude decays. This is because of the T2 relaxation. Therefore, if we can fit this echo amplitude, you repeat this experiment with the different values of T, you generate an exponential decay of the type which is shown in that curve, in that plot. Then you fit this to an exponential decay, you will be able to measure the true T2 value. So therefore, this is an extremely important concept which is useful in all kinds of multipulse experiments. Okay, so I suppose these ideas are, I mean, is it, are the interruptions, questions, answers allowed during these seminars? Anybody can ask questions here or something?
Like
interactively?
You can
Sorry?
ask. Yes, you can allow students to ask if they are.
So what I will do is I will ask if there is anybody has any question. Maybe I will take that at this stage. If somebody has a question, because that interactively it will become clearer.
Okay, participants, I think you can ask your questions if I having any questions.
If anything is unclear, if there is, you can ask questions.
Yeah, you can interact.
Yeah.
Rohit? Hello, Rohit?
Yes, sir.
So you can unmute the participants so that they can
Yes,
ask.
sir.
with the light.
Yes, I have unmute. I have unmute to all participants.
All participants, yeah. Okay, participants, if you are having any doubt, you can ask at this stage. Otherwise, sir will continue.
Yeah. So this is quite an important concept, this spin echo. This will appear again and again. Okay, so it looks like everything is clear. Yeah,
Seems like no one is asking, so maybe
somebody is asking.
no, sir.
Okay, fine. So we'll continue.
Okay.
Okay, all right. So now let's look at this phenomenon a little bit more carefully. Consider a two-spin system. Okay, now I'm going to explain this spin echo. So far, I explained the spin echo with regard to a chemical shift alone. Okay, there was no coupling involved. All the individual spins were singlets, so there was no coupling. Now we have to consider the system if there is a coupling. Consider an AM spin system. That means it is a two-spin system with a coupling constant. The coupling constant is J. Right? So now, if you draw the energy level diagram, I suppose this has been drawn earlier as well in the previous lectures. For a two-spin system, we draw an energy level diagram like this. Okay, you have the ground state here, where the two spins M and A are in alpha state, and then you have the beta alpha state here. Then you have the alpha beta state here. Then you have the beta beta state here on the top. So this has the highest energy. Okay, so in this, if you order the energies in this manner, okay, this typically this is drawn for a homonuclear system, but if there is a heteronuclear system, these two energy levels will not be so close to each other, they will be very far from each other. So one will be up there, so so this will be, and this other pair will be much higher, somewhere here one can draw. Okay, so now how many transitions? See, you know the selection rules. What sort of transitions are possible? The M value here is +1, magnetic quantum number. This is +1. This is 0. This is also 0. This is -1. So I will have a transition possible from here to here. And which transition is this? Here is the M spin is flipping from alpha to the beta state. Therefore, I call this as the M1 transition. And here also it is the M spin which is flipping. Therefore, we call it as the M2 state, M2 transition. Okay. The A spin has the same polarization, that is beta. In this case, the A spin has the polarization alpha, and here the A spin has the polarization beta. Now, these two energy differences will be slightly different because of the different polarizations of the A spin. And that is what is indicated here. If you look at this M1 and M2, for the M1, A is in alpha state, and for the M2, A is in beta state. Similarly, for the A1 and A2 transitions, the M spin is for the A1 transition, M is in the alpha state, and for the A2 transition, M is in the beta state. Okay, why is this important? We will see that. Okay, now suppose I apply a 180-degree pulse, because you remember in the pulse sequence of the spin echo, you had a 90-degree pulse, then a 180 pulse, and then the echo. Now, when we are talking about transitions, we are talking about the magnetizations in the transverse plane. Okay, so magnetization in the transverse plane is they are going with the specific frequencies M1, M2, A1, A2, etc. Okay, now what happens here? So suppose I apply a 180-degree pulse only onto the M spins. I'm not applying to the A spin. Suppose I apply only to the M spin. So what will happen? M spin will get flipped, right? Here now becomes beta M, and this becomes
We are not getting your voice.
Yeah, sorry.
It is coming now.
I cannot hear you.
Yeah, it's coming now. In between, your voice was not coming. That's what I want.
Voice was not coming. Is it coming? Is it okay
coming
now?
It is coming now. Yes.
Okay. So if you see here, when I apply a 180-degree pulse on the M spin, this state becomes beta M alpha A. This state becomes alpha M alpha A. this state becomes beta m beta A, and this state becomes alpha m beta A. You can see my cursor, right? I am moving the cursor so that it is the pointer I am moving as
The
I am
cursor.
explaining.
We can see the cursor.
You can see the cursor, no, because it should be clear what I am saying. Okay. So therefore, the energy levels have changed here. What is the meaning? See, this was M2 transition earlier. Okay. So the M1, this was here. As a result of that, what is the consequence of that? What has happened? Now, what was the A1 transition? The A1 transition was here, you see, for the A1 transition, the M spin was in the alpha state. For the A2 transition, M spin was in the beta state, right? So these two. Now, if I flip alpha to beta, what will happen? A1 goes to A2. A1 goes to A2, A2 goes to A1. So in the rotating frame, if I am sitting, one which was going faster with respect to the center will now start going slower, and which was going slower will start going faster. Suppose I sit here in the center. Sit here in the center. Now A1 was going in one direction. If I consider this as slower and this as faster, so this one is going slower, this one is going faster, or vice versa. It doesn't matter which way you consider. Now if I flip this alpha and beta, how do I do flip this alpha and beta? I apply 180-degree pulse on the M spin. This is what I did here. Okay. So then the A1 gets converted to A2, A2 gets converted to A1. That is indicated here. Okay. A2 was here, A1 was here. Now A2 comes here, A1 goes there. Okay. So what is the consequence of this? We will see in the next slide. Okay. Now here you see, again I put the spin echo sequence on the top. 90-degree, T, 180, T, and the FID. Let us start here after the 90-degree pulse. We will look at the A transitions there. The two A transitions are moved. I was sitting in the center of the chemical shift of A doublet. So with this, there is no chemical shift evolution. We are only considering in the J evolution. The two transitions are moving away. A1 is a transition which is A1 is this transition is just moving away in this direction, moving in this like, and A2 is going in the opposite sense, because one is going faster with respect to the center, the other one is going slower. Now, if I apply 180-degree M spin, A1 gets converted into A2 and A2 gets converted into A1. So you see what happens here. See, this A2 goes here and A1 comes here. But the sense of movement goes like this. A2 goes like this, and that is continuing. It was going like this, it will continue to go like that. And this was going like this, it will continue to go like that, because this is going in the anti-clockwise direction, this was clockwise direction, they will continue to go like that. And now if we wait for the next period, tau, t, they will come back and meet here, right? But what we will do is, we will apply 180-degree pulse on the A spin also. It is not only on the M spin, we are applying a 180, it is a non-selective pulse, we are applying on the A spin also. So when I apply the A spin 180 degrees along this axis, this fellow moves here, this fellow moves here, as indicated here. A2 comes here and A1 comes here. Okay, now this will continue to move like this, and this will continue to move like that. So in the next period, tau, t, they don't come back together, but they move further apart. Okay, they have come further apart compared to what it was here. Now, because I have applied a 180-degree pulse on both of them, they are moving apart. They are going further away from each other. So therefore, what it means is, if there is a coupling, the spin echo does not refocus J coupling evolution. The spin echo refocuses chemical shift evolution. It refocuses heterogeneities, field inhomogeneities, but it does not refocus J coupling evolution. This is an important concept one has to understand and remember it. Okay, so I explained this to you in principle. If you want, I can repeat that. So if it is clear to everybody, you can, because this is very important to understand. Applying a selective pulse, 180 pulse on one spin, flips the transitions. The one which was going faster goes slower, one which was going slower goes faster. Because the energy levels, you can see, you saw here, two transitions are flipped. One which was A1 has now become, one which was A2 has now become A1, one which was A1 has now become A2. Okay, so therefore their speed of precision with respect to the center, that will the interchange, but the sense of direction will not change. They will go in the same direction, and because of that they don't refocus but they separate away farther from each other. Therefore we say the spin echo does not refocus J coupling evolution. Excuse me, 1 minute. Hello? Hನುಮೇಗೌಡ. Yeah. ನಾವು ಲೆಕ್ಚರ್ ನಲ್ಲಿ ಇದ್ದೀನಿ ಹನುಮೇಗೌಡ. ನಂತರ ನಾಳೆ ಮಾತಾಡಿ. ಇದು ಲೆಕ್ಚರ್ ಒಂದು 7:30 ತನಕ ಆಗುತ್ತೆ. 6:07 ತನಕ. ನಾಳೆ ಬೆಳಗ್ಗೆ ಮಾಡಿ. ಬೆಳಗ್ಗೆ ಮಧ್ಯಾಹ್ನದಲ್ಲ ನಾನು ಹೋಗ್ಬೇಕು, ಹೊರಗಡೆ ಹೋಗ್ತೇನೆ ನಾನು. 10:10ವರೆಗೆ ಮಾಡಿ. ಓಕೆ. So you see, I've indicated that here in another schematic diagram here, HX spin echo. So far I consider the two spins A and M, they were both homonuclear, both of the same type, right? So if I apply 180 pulse, I am applying to both the spins A and M. Suppose I have a hetero system. Now the two channels are different. Proton channel and the X channel are different. So that typical spin echo which I considered there, which I explained to you earlier in the previous slide, is now in this situation. For this, on the top portion of this slide, the 90-degree pulse is applied on the proton, but the 180 pulse is applied to both the channels, proton and X. Okay, so in this situation, when at the echo time the coupling constant is not refocused. Okay, coupling evolution due to coupling between proton and X is not refocused here, but the proton chemical shift is refocused at the echo. Okay, proton chemical shift is refocused because this tau and tau are the same. The proton chemical shift is refocused, but the proton coupling is not refocused here. Now suppose what happens if any of the 180-degree pulse is dropped? Suppose I drop this proton pulse. It doesn't matter if I drop this also, either way. If I do that, see, look what happens here. So two transitions of proton are here. They are going away during the period tau. They are moving apart like this. Now I apply 180 X pulse. They get interchanged. This comes here, this goes there. And they will continue like this. This will go like this. And the next tau, it will get refocused. Okay, so if I apply a 180 pulse on one of those only, this means the coupling is refocused. This is amounting to HX decoupling at the time of the echo. Okay, the same thing will be true if I apply 180 pulse on the proton also. But in that case, of course, I am refocusing the chemical shift of proton as well. Here I am not refocusing the chemical shift of proton. I am only refocusing the coupling. So the coupling is removed, but the proton chemical shifts will continue to go at the time of the echo, not afterwards. Afterwards, of course, everything will evolve. You have not done nothing here. So during the FID, all the couplings, everything is ineffective. But at the time of the echo, when I say the echo amplitude modulation will have the J coupling evolution, and it will have the chemical shift evolution, of course. Okay, so when I monitor the echo amplitude, then this is what applies. So at the time of the echo amplitude, the HX coupling is removed. Okay, so maybe I think it is a good time to stop here. Haridas, take a break for a few minutes, 5-10 minutes.
Sure, sir. Yeah, you can make a small break now.
Yeah.
Then you can start maybe.
So we'll think about, you can have some tea or coffee or something, somebody, and we'll come back in 5-10 minutes, 7-8 minutes.
All right, participants. So a small break now, after maybe 5 minutes or 10 minutes, sir?
Yeah, 5 minutes.
5 minutes. Okay, after 5 minutes we rejoin. Hello, Rohit.
Yes, sir.
You are there, no? So Sarah has taken a small break, 5 minutes. He'll restart again. Okay, so you'll be
Okay,
there.
sir.
Okay, fine.
Okay, so I am back. So can we?
Yes, sir, you can start.
Okay. So now we make use of these concepts. So discuss about some of the practical experiments. One of the most important among all of these for the carbon 13 users, there is an organic chemist attached proton test. That is, you want to see whether a particular carbon is attached to a proton or not. This is simply using this PEN-ECHO sequence which I indicate here. So this sequence has the simplest one. There are many ways one can perform an attached proton test, but this is the simplest way to understand the concept here, what is happening. So you have here a proton channel and a carbon channel here. You apply 90-degree pulse to the carbon. Here you remember you are measuring carbons here. You are not measuring proton. You are measuring carbon. So therefore the FID which you are collecting is the carbon FID. Okay, various carbon signals. So therefore you start with the carbon 90-degree pulse. Wait for a time tau. Then you apply a 180-degree pulse along the y-axis. And you simultaneously apply a 180 pulse on the proton channel as well. Okay. Then wait for the same time tau. And then you do a decoupling of the protons. All the protons are decoupled and you acquire the carbon frequencies. This is the experiment. Okay, very simple experiment. Let me repeat it. You start with a carbon excitation with a 90-degree pulse. Wait for a time tau and apply a 180-degree pulse onto the carbon channel. and simultaneously on the proton channel a 180-degree pulse. Then you wait for the time tau again, and then you decouple the proton, acquire the carbon signals. Of course, during this period, before the 90-degree pulse, and what happens here, there is a so-called relaxation delay. You can decouple the protons also. There also you can decouple, although there is no magnetization there, but that is, you can decouple the proton, but it has a particular advantage that we will see later. That is from the point of view of NOE, that some decoupling will be helpful. So you notice here, therefore, this is the spin echo sequence, right? So 90, 180 tau, this is the spin echo sequence. 90 tau, 180 tau, this is the spin echo sequence. Here we are getting the carbon echo. And we are applying the 180 pulse on both the channels. Therefore, a carbon chemical shifts are refocused at the time of the echo. 90, 180 on the carbon means the carbon chemical shifts are refocused. A simultaneous 180 pulse on carbon and proton means the carbon proton coupling is not refocused. So at this point, that coupling modulation is there. This echo amplitude is modulated by CH coupling evolution. Okay, how does it show up? These are two different ways of performing this attached proton test. As I said, you can also do it in this manner. You decouple the protons here, but this is for the purposes of NOE, and you can do a 90 pulse on the X, decouple the proton, and you, after the 90X pulse, you wait for a period delta. You apply 180 pulse Y on the carbon, but you don't apply 180 pulse here, but you do a decoupling. Decouple all the way from here to here, and during the period delta, you put the same period delta here, and you start acquiring the data of carbon here in this manner. This is another way of doing the same thing, but the easier thing to understand is this, which I mentioned. The decoupling here, what we achieved by this one is, there is a decoupling applied here. You want to evolve the carbon proton coupling for the period delta. Okay, and the same thing is applied. See, the total period is delta here, right? Delta by 2, delta by 2. The CH coupling evolves for the period delta. The same thing happens here. CH coupling evolves for the period delta. After that, it is not. After that, it is decoupled. After that, the CH coupling does not evolve. So the decoupling here. Then you collect the data. This, of course, requires more time because you have two delta periods here. Here, there is only one delta period overall, and you acquire the data at the end of the delta. Now, how do the different carbons behave? Depending upon the delta value we choose, how do the different carbons behave? That we can easily visualize here by this vector picture, by this diagram here. Look at this diagram very carefully. Try to understand this. I also shown here the carbon multiplets on the side here. This is the carbon, this is the singlet carbon. This is a doublet carbon, one proton attached. And this is a triplet, this is two protons attached. And this is a quartet, this is three protons attached. Okay, 1:3:3:1 here, 1:2:1 here, and this is a doublet. Let us look at what happens in this. The carbon, after the 90-degree pulse, the magnetization is along the y-axis. Okay, and the chemical shift of, there is no coupling evolution of the singlet. Okay, therefore nothing happens to it. It remains here only, no matter what the delta. This is what is given on the top here is delta value. Delta 1/4j, 1/2j, 3/4j, and 1/j. Four different values, intermediate values. The evolutions of the individual multiplets is shown here. So far as the singlet is concerned, nothing happens to the singlet because there is no coupling evolution. Chemical shift is refocused. Therefore, it remains where it is. So all along this singlet, carbon remains along the along this axis, the y-axis. Now look at the CH carbon. CH carbon, because of the coupling, it has the two plus minus components. See here, plus j/2 and minus j/2. The separation between them is j. Okay, and they are moving here 1/4j, up to 1/4j. How much angle this has covered? This has covered 45 degrees. This is 45 degrees. Okay, so therefore the total separation here is 90 degrees. What does this depend upon? The separation depends upon how much evolution has happened. What is the frequency of evolution here? J/2, and the angle covered is 2 pi times j times this delta. Okay, 1/4j. So therefore, this will be 2 pi, this is j by 2, okay? 2 pi times j by 2 times 1 by 4j. Therefore, it is pi by 4. This is 45 degrees. This is 45 degrees. Therefore, this is 90 degrees. If we make it 1 by 2j, then of course they become antiphase here. They are along this axis. When you go 3 by 4j, they continue to move. They come here. So this is 45 degree now. This is 45 degree. And at 1 by j, they will come back and join here. And therefore, these plus minus, they will come back and refocus along the negative y-axis. Whereas the singlet carbon remain on the positive y-axis, the CH carbon comes on the negative y-axis. Okay. Now let's look at the CH2. CH2 has one frequency at the center. Okay. So this central frequency doesn't matter at all. This doesn't move. Okay. This is chemical shift. Chemical shift is refocused. Therefore, it stays there only. That's zero. That is the zero frequency. That is indicated as zero. Okay. And what about the other two? These ones are, this one is J here. This separation is J here. Now let us look at what happens here. Now those two, if we are considering these two transitions, this have moved to these positions just as here, right? They have moved to this position because now the frequency here is J and here it was J by 2. Therefore, they have moved to this position here at 1 by 4J. And at 1 by 2J, they are moved back here to this refocused here. Okay. Minus plus, and 3 by 4J, minus comes here, plus comes there. And at 1 by J, they all come back here in this position 0. So therefore, 0 plus minus, they all come back along the y-axis once more. Okay. Now look at the CH3. The CH3 has 4 lines. Okay, the center is here. The center zero frequency remains at 0. There is no frequency at 0. Okay, here there is no frequency. So I have here a J by 2, J by 2. Then I have here 3J by 2 and 3J by 2. This separation is 3J by 2. This separation is 3J by 2. This is J by 2. This is J by 2. Therefore, these 4 components move in this manner. Initially, all of them are like this. Now, you see here, you have the minus these two. This one is J by 2. This is 3J by 2. This is again J by 2. This is 3J by 2. They have moved here, 1 by 4J. Now, at 1 by 2J, they come together here at along this negative y-axis. They continue move in the circle. There is a reflection of this here. So, from here, they moved this minus come on this side, plus come on this side. Notice the change in the orientations. Okay. And then after 1 by J, they all have come back onto the negative y-axis. Where is my cursor? Okay, they all come back to the negative y-axis. Therefore, what you see in this, if I keep my J, if my delta is equal to 1 by J, the singlet carbon will be along the positive y-axis. CH doublet will be on the negative y-axis. CH2 will be on the positive y-axis. And CH3 will be on the negative y-axis. Therefore, I must see a change in the coupling is refocused, all of them focused, but they are refocused along the different axes. Now, the same thing is a little bit more quantitative here, indicated for different values of J, the different values of delta. So, calculation is done according to this. So, this is the carbon, singlet carbon remains like this, no matter what your this theta is equal to pi j delta. All the 4 carbons, they follow this equation here. Carbon goes as I is equal to 1, doesn't change. CH is proportional to cosine theta. CH2 is proportional to cosine square theta. CH3 is proportional to cosine cube theta, because there are 3 carbons, each one of the 3 protons. And you plot that graphically here, depending upon the angle theta, what is the sign of the signal what you are going to get. This is intensity. This is positive here and negative here. Okay. Before 90 degree, all of them are positive. See, all of them are positive. There in the previous picture, I showed you for 4 particular values of delta. 1 by 4J, 1 by 2J, 3 by 4J, 1 by J. to able to explain this in a vectorial manner, picture-wise. But you can actually do a more quantitative calculation for any value of delta. The value of delta can be, it results in a particular value, angle called as theta. This is pi j delta. This is the theta value. So depending upon the theta value, different carbons would have evolved to different degrees on the positive atmosphere or the positive hemisphere or the negative hemisphere of the circle, semicircle, or the upper semicircle or the lower semicircle. So here you see, if I have a 90 degree, all of them are 0 except the C. At 90 degree, yj delta is what is the meaning of 90 degree? Delta has to be equal to 1 by 2j. If it is 1 by 2j, then this is pi by 2. When it is pi by 2, cosine theta is 0. Therefore, all of them are 0. Therefore, you see a 0 here. Do you see that here in this picture? If I take 1 by 2j, singlet will go on. Okay, nothing changed. But you see all of this. This is positive, negative, this will cancel. Nothing here. Same, this will cancel. Okay, on opposite sides. And here also it is the same. They will cancel. Nothing here. So therefore, this is clear that you will have 0 signal when you have 90 degree this. And if you have 1 by j, which is the last picture of that, 1 by j means I should have delta is equal to 1 by j. Delta is 1 by j means I have a theta is equal to pi. Then pi means, so this one is 1, cosine pi is -1, square of that is +1, cube of that is -1 again. Therefore, CH3 and the CH will appear as negative. You can see here, CH3 is this, CH is this. This will appear negative at 180. And CH2 is cosine square, that will be positive. That will be here. CH2 is therefore positive. So therefore, you can see now that depending upon what kind of a multiplet it is, what proton it is, and how many protons are attached to the carbon, you get different signals. And this is precisely what is used in all of these kinds of experiments, attached proton test. After that, you decouple. During this, so what happens next? After that, you see, and they are refocused here. This is the initial condition. You reached at the time of the echo. At the time of the echo, whatever is the condition is there. So if it is a positive signal, positive echo or negative echo. You will have a positive echo in case of CH3 and a negative in the case of C and CH. What was that? You have positive echo for C and CH2 and negative echo for CH and CH3, right? So therefore, and then after that you are decoupling. So when you come here at this point, there it is. So at this point, so you have the positive echoes and the negative echoes for the different carbons, and after that you are decoupling the proton. Therefore, no more evolution of proton-carbon coupling happens. So whatever is the condition here, it will show up in your spectrum in the fully decoupled carbon spectrum. Carbon spectrum, therefore, will have positive and negative signals. And that is shown here. So this is the fully decoupled carbon spectrum without the attached proton test. This is not the APT sequence. Okay. Now here you have for the same molecule. So from this you cannot make out which carbon is what, because it's the fully decoupled spectrum. In the earlier case, when we used off resonance decoupling, there of course on the basis of the multiplets, we are able to figure out which carbon is what kind of a multiplet it is. Whether it is a doublet or a triplet or a quartet, we were able to figure that out. But in complex structures such as this, there will be lots of overlaps. You may not be able to figure out that even in the off resonance decoupling. But if you do this experiment, you are decoupling all the protons. So you're getting singlets for each one of those, but then you're getting different signs of the signals for different carbons. So the ones which are here with proton, so CH2 and C are positive. In this is the bottom, the blue one is the APT spectrum. Okay, these are all positive. Forget about this. This is the chloroform CDCl3 signal, and this is all positive. and this is the singlet here. The singlet, this must be the carbonyl or something, 140, whatever that is. So these are all CH2 and C, okay, positive signals. All the negative ones are CH and CH3. Of course, you don't know which is C and which is CH and which is CH3. So you can distinguish up to this level. Of course, then you can do further tuning of the delta value, and then you can actually see differences in the intensities of the signals, and that comes from here. See the CH2, CH3 and CH, they have different values. If you take 135 here, for example, then I will have different intensities for CH and CH3. Both are negative, but then they're different intensities. At this point, they have the same intensity. Therefore, you can't make it out. But if you're taking a value of 135, this is here, then you have different intensities for the CH and the CH3. And CH to C, anyway, this can be distinguished. This has different intensity compared to this. Okay, C is highest, then you have somewhere midway here, then you have the CH2, CH3 here, and the CH here. So by approximately adjusting this delta value, you can figure out which kind of a carbon it is in the APT test. Okay, so now I will move on to the second. This was actually part of the first lecture. So I will close this and open the next PowerPoint. Okay. Next lecture. So I should close this. Oh, I went out, is it? Can you see my slide? Am I on? Hello?
Yes, sir. You can see it.
You can see it. Okay, fine. So now I open the next PowerPoint file. So we continue from there. And now we talk about that was the attached proton test. Okay. That is to find out what were the carbon, what kind of carbons they were. So now we move on to polarization transfer. This is the general phenomenon which is extremely useful in carbon NMR and also in other cases, heteronuclear experiments. You can do polarization transfer from a more sensitive nucleus to the less sensitive nucleus, from the proton to the carbon, or from the proton to the nitrogen, and so on and so forth. How is this done? There are many ways of doing it, and the fundamental one of that is called the selective population inversion, SPI. How does it enhance the signal of a less sensitive nucleus, borrowing the magnetization from the more sensitive nucleus? So to understand that, let us see the diagram here, and we will see how one can perform this experiment and how to gain the sensitivity. Selective population inversion. What is the meaning? So you consider a two-spin system here. Two-spin system, the AX spin system. Therefore, as before, I have two transitions for the X, X1 and X2, and A1 and A2. Okay, this is for the A transition. Now let us assume that the populations of these states are as indicated here, delta plus capital delta plus small delta. This is minus capital delta plus small delta. Then this is minus delta, and this is capital delta minus delta. So now what will be the populations, what will the intensities depend upon? intensities are proportional to the population differences, right? So let us look at what is the intensity of the X1 transition. X1 transition is this. So it will depend upon the population difference between this level and this level. And so if I take the difference between these two populations, it is proportional to 2 times delta. Similarly, 2 times small delta. Now, similarly, if I take the population difference between these two levels, levels 2 and 4, once again, it is 2 times delta. So therefore, these two levels are equal. Now, notice here, this small delta is smaller in number compared to the big delta. Delta is a bigger number. Okay, particularly this is important in the case of heteronucleus experiments, because the energy separation is proportional to the gyromagnetic ratios, and therefore they will have different population. These two levels will not be the same in the case of heteronuclear system. For example, if you're taking carbon and proton, this capital delta would correspond to the population difference for the proton, and the small delta would respond to the population difference of the carbons. For example, if I look at the A1 transition here, the A1 transition, what is the separation? This is 2 times capital delta. And similarly, A2 transition is 2 times capital delta. And these are the proton transitions, for example. Okay. Therefore, this capital delta is larger than the small delta. Although these are both 2 delta, 2 delta, the capital delta is much larger number compared to the small delta. And this is assume that this is for the proton and this is for the carbon. Okay, these intensities are much smaller and these are much larger. Now what I do is I apply a selective inversion pulse to this A1 transition. 180-degree pulse is applied to this A1 transition. That is indicated here. If I apply selective pulse, here I have indicated those energy separation more clearly, right? You can see this. This is the carbon. This separation is carbon. This separation is proton. Therefore, this population difference is larger than this population difference. Okay. So this is clearer here. Okay. Now you apply a selective inversion pulse on the A1. What I mean inversion pulse? I invert the populations. This population goes there and that population comes here. In fact, they already indicated that after applying a 180-degree pulse, delta, this population was here in the previous slide. Now that has gone here. What was here has come here. So this is minus delta plus delta. This is capital delta plus delta. This is what I have done. Okay. After the 180-degree pulse, these are the new populations now. What I indicated here are the new populations. Now let us calculate the intensities. Intensities of the individual transitions. And let's look at the first, the A1 transition. A1 transition is this minus this. Okay. So that is minus 2 delta. So that is down here because it is minus sign. And A2 transition, this is this minus this, that is plus 2 delta. So that is here. That was the same as before. Nothing has happened to that. That means I have selectively applied an inversion pulse to the A1 transition only. Okay. Now let's see what happens to the X transitions. Now X transition, this was the intensity separation between this level and this level. What is this separation? Okay. Minus 2 delta, 2 capital delta plus 2 small delta. Okay. This minus this. Minus 2 capital delta plus 2 small delta. And this one is 2 capital delta plus 2 small delta. So look here, there is a huge change in the intensities. Earlier there were only 2 delta, small 2 delta. Both were small 2 delta, and now they are overwhelmingly against minus 2 delta plus 2 delta. This actually has lost on the negative side, gained on the negative side. This has gained on the positive side. These two, therefore, intensities are not equal anymore. So this one is minus 2 capital delta plus 2 delta, and X2 is 2 delta capital delta plus 2 small delta. This has gained in intensity quite a lot. And therefore, by inverting one pulse or one transition of the A spin, which is more sensitive nucleus, for example, it is a proton, then I have actually gained the intensities for the X transitions. Okay, therefore, this is called as selective population inversion. Is that clear to everybody?
Yes, participants, you can,
If I keep getting some feedback, it will be useful.
yeah, you can,
Participants, then I will also know that they are attentive.
Yes, sir, it is clear.
It's
okay,
clear.
good. Try to respond.
Yes. Okay. So therefore, there is a huge gain in the signal intensity. So this same principle is used in another experiment called as inept. Okay. Why did we have to do this? Let's see if there is any difficulty here. There is no difficulty per se, except that you must be able to apply a selective pulse on the A1 transition. If you are not able to apply selective pulse, then the whole gain will not be there. What is the difficulty in applying a selective inversion pulse? Remember, this coupling constant is of the order of, let's say, 100 hertz. So your selectivity should be such that the A2 transition should not be affected. A2 transition should not be affected. So in other words, your excitation bandwidth should be something like about 10 hertz or 20 hertz, not more than that. Notice then this excitation bandwidth will be acquired only if you apply the pulse for a long time. If you apply a hard pulse, like a 10 microsecond pulse, you will excite about kilohertz of frequencies. So if I want to excite only 20 hertz, then my RF should be applied. The inversion pulse should be of the order of a second of a 500 milliseconds. Okay, or 50 milliseconds, 50 milliseconds or 60 milliseconds, 100 milliseconds, depending upon the range I want to use. So 100 milliseconds is a long time for an RF pulse to apply. So that will increase the length of your experimental sequence. How many you will do? There will be relaxation phenomena happening during these 100 milliseconds. During the pulse application, there will be disturbance. The relaxation will happen. So all kinds of problems will be there. Therefore, selectivity causes these issues. Selectivity of a transition is difficult to achieve, and when there is a crowded spectra, anyway selectivity is not possible. When the lines are very well separated, you can apply, yes. When the lines are very well separated, there is no difficulty, even though you have to apply for a long period of time. If you want to get 10 hertz excitation, they have to apply 100 milliseconds. This is, and then if I want to get 5 hertz separation, then I have to apply 200 milliseconds. So this will be a huge increase in the pulse width. And typically RFs you don't apply for that long. Pulses do not apply for that long, then they will not remain stable for that long period of time. So there are technical problems when you want to apply selective pulses. But hard pulses are easier to apply, and it is not necessary to optimize anything there. When you are applying a selective pulse, you must be very careful that you apply your RF just at that frequency, not anywhere else. So you must choose your select RF exactly at that value. So you require a pre-knowledge about the frequency where you want to actually apply. And that is a hard thing to do. And in this case, you can apply it only one at a time, right? So, and this actually is the limitation of the selective population inversion, but the concept is very good. Now, if I can achieve the same concept by using a hard pulse, then it will be much better for me. Okay, fine. That was the philosophy of this experiment called as insensitive nuclear enhancement by polarization transfer. This is called as inept. Notice here, again, we are observing the carbon signal, the X signal we are observing here. But we start the pulse sequence in this manner. We use a spin echo sequence here. Okay, you start with the proton 90 degree here, wait for the period tau, then you have the 180 degree pulse on the proton as well as on the carbon. Then you apply a 90 degree pulse on the proton, 90Y pulse. Notice here, this is important. If you apply a 90X here, you must apply 90Y here. And then you apply a 90X on the X, and then you detect the signal. Okay, and notice there is no decoupling possible in this. Here they are not making any decoupling. We will see the reasons for that. You acquire the FID immediately after this 90 degree X pulse. Okay, so clearly this is a spin echo sequence. Okay, you are exciting the proton, do a spin echo on that one. The protons are refocused at this point. Proton chemical shifts are refocused, but the proton coupling is not refocused. because you apply 180 pulse on both these channels. 180x here, 180x here. On both the channels you apply 180 pulse. Therefore, the proton, carbon or X nucleus, whatever it is, this is not refocused at this point. Okay. So that is the first principle to know. And what happens after that? We will see. So consider, now again I am taking the same AX example. A is the proton and X is the carbon. Assuming I have applied after 90-degree pulse on the proton. So at this point in time, I have the two transitions A1 and A2 here along the minus Y axis. During the next, I give tau period. Let us say I give a tau period of 1/4J. I discussed this previously. When I talk about the spin echo, I had the same discussion, but I put those numbers, I explained that here. The same thing happens here as well. So the separation between these two is 2 pi j times tau. So if I say tau is equal to 1/4j, then what do I get? I get this as pi/2. The separation between them will be pi/2. This is 45 degree here, 45 degree here. So this separation will be pi/2. Now I apply 180 pulse on the A transitions. Okay. Therefore, then this will move here. This will move here like this. A2 will be here, A1 there. And then apply a 180x pulse. So now there is a switching. So this goes faster. There will be change in the direction of the movement. Okay, this will become one which was going slower. They change the sense of direction. Is the same thing as saying A2 goes there and A1 comes here. Instead of saying what I have done here is I kept the same label A1, but I changed the sense of motion. This goes in this direction, then this goes in this direction. Okay, it is equivalent to saying A2 goes there and A1 comes there. Both are same. So now during the next tau period, these ones would have moved another 45 degrees. So they will then come here and in this direction, A1 and A2. See, now you see along on this axis, they are opposite in direction. Okay, the two transitions are opposite in direction. Now we apply a Y pulse. These were along the X direction now. This is X and minus X. Okay. If I apply a Y pulse on the proton, what will happen? These things, one will go here, other one will go down. Okay. A1 is going up, A2 is going down. What is the meaning of this? The meaning of this is I have applied a selective 180 pulse on the A2 transition. I've inverted the magnetization of A2 corresponding to A2. Selective inversion of the A2, because both are, what is along the Z axis represents the populations, right? What is present here is the population difference corresponding to the A1 transition. What is present here is the population difference corresponding to the A2 transition. In the selective population inversion, this is what we did. We inverted the populations. Okay, populations of the two. And then actually we saw the signal intensities. When you apply 98 pulse afterwards, you measure those intensities. So these population differences. So the population differences have now become, see, essentially initially both were here to start with. I inverted the populations corresponding to the A2 transition, and therefore the A2 has come down here. This is exactly like the selective population inversion. Now, therefore, as a result of this, what has happened? The two X1 and the X2 transitions have changed their populations. Okay, X1 and X2 transitions have got different populations now. So I have schematically indicated here the two things. When I apply the 90x pulse on the X spin, now they will come along different directions like this, X2 and X1. Although I have schematically shown here as equal in intensity, they are not equal in intensity as I indicated in the previous slide. They will be slightly different. 2 delta plus 2 delta minus 2 delta plus 2 delta. That was the kind of intensity what we will have here. That will be clear in the next slide. So therefore, it is clear that now I achieved the same purpose as in the case of selective population inversion, but I have used now a hard pulse. I have used a selective pulse. I've used a non-selective pulse on the proton channel, and we have transferred the magnetization to the X transitions, and the two X transitions are in opposite directions. Okay, now this is going in the same. You have to continue this. Dr. Paul, when do you want me to stop? How much time? This is now 6 o'clock.
It is already
Should we
6 o'clock.
should we
So maybe
Huh?
how yeah, it's up to you. You want some more time?
This will go for long.
Actually, we
So
can
this one,
up to certain point where you feel
what I can do
stop,
is,
you can stop there, right? Actually,
so this is inept. I explained this
is the
inept.
point where you can. It is better to stop. You find out that point where you feel that is you can stop there.
Yeah,
You can stop there. Actually,
yeah. Let me see.
it should
Yeah.
not hamper in the
No,
continuation.
actually, probably after this slide, I will stop.
Okay, you shouldn't hamper the continuation.
Huh?
You should not hamper the continuation.
Yes, correct.
That part you.
This is the continuation of that. Yeah, this is the continuation of that previous one. So I will stop after this.
Okay, sir. Okay.
Okay. So you see
Okay.
again, the same thing is indicated a little bit more explicitly in this slide. See, proton 90, 180 Y, 90. This is 180 X, 180. I already explained this to you in this case. So in the same curve diagram is given here. Okay. 90X brings magnetization here. And then of course 1/4J, the two things separate out, the fan out. Then the 180X pulse on the X brings the two transitions here, because this goes here and this goes there. And then apply 90 and then 180 pulse also on the X, interchanges those two, I get here. And then as the result of this, I will have the coming down to 1/4J. This will and go up here. Okay, now what is indicated here is the initial magnetization of the X spin also. X spin, since I applied a 180 pulse here, at that point, this X spin magnetization has come down onto the negative Z axis. Okay, so here the X spin transitions are also indicated there. And then at this point, the next 1/4J, these two transitions come here. Okay, they align along this axis. So 2 and 1 are here. Then when I apply the pi/2y on the proton, they go up and down as I indicated in the previous slide. This one, this 2 goes up here and 1 comes down. Okay, these two are equal intensity, but these two transitions, the X transitions which are there, see now they are on the Z axis, but they are now with the different intensities. This is what I indicated earlier in the selective population inversion. Okay, so this is the selective inversion. This is the selective inversion of the A1 transition of the A spin, and the X on the X2 transitions have acquired intensities like this. Okay, now we apply a pi/2 X pulse to the X spin. They come out in this on the transverse plane like this, and then I collect the data, detect the data on the -y axis here. So you get an FID of this, but now after you will see the two transitions of the X spin coming out like this with a slightly different intensities, which is what we saw in the case of SPI. So this is the clear representation of the SPI effect coming in the inept. Okay, so and that is how you achieve a significant gain in the intensities of this, but with a different sign pattern. Okay, so this is what is insensitive nuclear enhanced polarization transfer. So you will continue from there onto the in the next lecture. So we'll stop here at this point. So unless there are any questions, any clarifications, so we can stop here.
Yeah, participants, if you have any doubt, you can just ask at this point. Otherwise, you can communicate with Professor Hoshur. His email ID is shared with you. So you can write to Professor Hoshur whatever your doubts are, so that in the next class he can explain a little bit about that. Okay. At this point, if you can identify some of your issues, then you can just ask him. Rohit, can you unmute all the participants? Hello, Rohit.
So Haridas, this is going well, isn't it? So with my
Oh, yeah, it is fine.
communication with the cursor, it is going well.
Yeah, it is fine.
It's fine. Okay, so then I don't need to write, so I can manage this with the PowerPoints.
Okay. You can manage it this way with PPTs only. And next
Yeah, PPT.
next Friday,
Yeah.
I feel you are coming to HBN, I know, sir.
I'm wondering whether if this is working well, then I can do it from here.
Okay, that let me know. If you're coming, then I've already initiated it, but to arrange the vehicle. I have already initiated that, but according to your
Initiated.
chart.
Okay. So I will just see. Okay, so this is of course in the next lecture. Of course, part of this I will continue from here. Then we will go on to the next lecture. So I will bring the laptop and the iPad. Maybe I will. Let me think about it.
Okay, take your time. Take your time, since the time is.
If I can manage with this PowerPoint, I was just checking if the PowerPoint slides are working well. If I'm able to communicate everything well.
Okay, sir. By tomorrow, if you communicate me, then accordingly we can arrange.
Okay.
Immediately we know to say. All right.
Yeah.
And for participants, do you have any queries at present? At least response yes or no.
No, sir. Sir, maybe we'll just read something and tomorrow we may ask question.
Materials, go through this once again,
Yes,
and if you have any doubt, then you can write to Professor Hoshur. He'll be happy to.
These slides can be made available to them. These slides can be made available to them.
Means they can see in the YouTube. If you can make it this one PDF file kind of thing, so that we can share with them as a reading material.
Oh, okay.
That you can share with us. You can send it to me, so we can put it in the site, so everyone will be having that access.
Okay.
That is one way of doing, because all the Dr. Ghosh did that way. He converted it to PDF file, and the PDF file was shared with the participants.
Yeah, I can send the PDF files to you.
Okay, that will be fine, sir. So sometimes send it to me so that I can upload it in the site.
Okay.
Okay, then thank you, sir.
Okay, thank you.
This is our next lecture on Friday in the same time.
Friday.
4 to 6.
Same time, yeah. So I will continue this. Yeah, right. Okay.
Okay, till then you get.
How do I quit?
Okay, participant. Till then you.
How do I quit? Where is?
Yes, sir. You wanted to
how
say?
Do I quit? Where is? What did you say?
No, how to quit? I think just you have to come
How
out.
to quit?
You have to close it. That's
Stop.
This.
Then but it is. I did not come. Did not quit. Share your screen. To stop sharing. I'm still connected.
You are still connected. You have to.
I'm still connected.
Yeah. You have to close it. You have to, from the top. Actually, if you cross.
Stop. If I say stop, I think that is what I'm leaving. Is it?
Stopping everything. Yeah.
Okay. Now stop video. Share. Mute. Okay. Here. Leave meeting. Okay. So I will leave the meeting now.
Okay, sir. Thank you very much.
Okay. All right. Okay. Thank you. See you.
So tomorrow you let me know if you would like to come. Then accordingly I will arrange it. Otherwise, if you are
okay.
in the home, then it's all right.
Okay.
Okay, sir. Okay, thank you, participants. Thanks a lot. Rohit? Rohit, I'm audible to you?